Welcome. We're in Explain 10 today, where I'm gonna shoot another video. I did a previous video in the Explain 11 beta, and in there I was checking out whether the IXEG 737 worked in Explain 11 beta. Did a video of the startup, and I had quite some views for that video already, so everyone who thought it was worthwhile to watch it, thank you very much. Mr. Fairy Cake asked me a question. Is it possible to the next IXEG video could explain in a bit more detail how to program the FMS a little bit slower and with some information on what you're doing for us nobodies? That would be very useful. Well, at least I can give it a try. So that's what we're going to do now. In Explain 10, as mentioned, I have better frame rates in Explain 10, at least in Amsterdam. Of course, I'm Dutch myself, so I completely loaded the simulator with all the Dutch scenery that I could find. So this is Aerosoft Amsterdam. Bought that one, and of course it's a fabulous looking airport, but it's also very heavy on the frame rates. I sincerely hope that Aerosoft will make an Amsterdam V2, and like they did with Frankfurt, and try to make it a bit frame rate friendlier, because it's a beautiful airport to fly from. It's one of the busiest in Europe, of course, and well, it's quite central, so you have a lot of destinations to pick from, and you can fly to most of them within 1.5 hours. So that's really nice for short haul flights. You can fly to the UK, Paris, Germany, of course, Belgium, Switzerland is 1.5 hours, Côte d'Azur is 1.5 hours, so it's really nice. But we are not here for the scenery, of course, so I already powered up the aircraft. I'm not going to do a complete startup tutorial. We already have that, so we're not going to do the double work. I just switched on the power, put it on the basic battery power, switched on the ground power, so the airplane is now very well powered. And then we will start showing what to do to program the flight management computers. So let's go. Um, First things first. This is the utility that we will be using. This, however, is not the flight management computer. This is called the Control Display Unit, or CDU, Charlie Delta Uniform. It's basically only the screen and the keyboard, and the actual computer itself is, well, buried very deep within the airplane. I believe there are, I'm not really sure. I thought there were two flight management computers on board, but could be wrong about that. Anyway, um, when you start up the plane, you see this FMC ACMS. Well, I don't know what the ACMS does, but we have to go into FMC, of course. When you enter the FMC, you start with the ident page. And in the ident page, you will find information about the type of aircraft, the data of your navigation cycle, the so-called AROC. Mine is from 2016-08 August. Well, as you can see, it's now December, so this is out of date. Well, I don't really care about that. The most important thing, however, is that if you use a third-party program to make your flight plans, make sure that you have the same AROC data in there as you have in the computer. Otherwise, the flight plans that you create in your third-party program are not compatible with the flight management computer, and you will get messages like this waypoint is not on this route, or don't know this waypoint, stuff like that. So that's really, really important. Of course, you can see the engine rating, operation programs, well, all stuff like that. And then you can do two things. You can go back to the index or to the POS init page. But let me tell you a bit more about the CDU first. Of course, this is the numpad. This is the normal keyboard, clear and delete. And here are also a couple of buttons, previous page, next page. Initref is initialization reference. RTE is route. CLB climb. CRC cruise. Descent. Menu goes back to the start menu of the FMC. The legs page, which shows all individual navigation legs. We'll get to that later in this video. The DEPR or departure arrival button. Here you can switch or set up the departure routes and the arrival routes for your for the airports in your flight. Hold, you can program holdings in here. Prog or progress. It will show you basically how far the flight is, how far you still have to go, and what the estimated time of arrival will be, how much fuel you will have when you arrive, etc. And one limit page, that's for the engines. Fix, here you can put in navigational fixes. That's quite handy in certain approaches. Don't think we'll use it today, but maybe sometimes I do another video of an arrival in Innsbruck, and then we can definitely use the fix page. Well, previous page, next page, that's self-explanatory. And the execute button. I hope that this is clear. These are the basics of this. We'll start with position initialization. And the first thing we have to do is actually not on the FMC, but it is on the IRS, which is in the after overhead panel. And that are these two knobs. They are now switched off. And of course, when we start flying, we have to navigate our way from the origin airport to the destination airport. So it's quite important that we have the navigation software online and aligned, and that aligning is what we do now. You switch both of these switches 2 clicks to the right to the nav position. So 1, 2 and 1, 2. It flick on DC and then to align. It must do that here as well. It does, so that's okay, checked. And if you turn this knob, then there is a stage. Well, not yet then. In real life, it is possible that you get a line here which says how long it will take. Oh, here it is, all the way to the right. It will take another 7 minutes for the IRS to completely align itself. Aligning, what is that? Well, if you start the plane from the cold and dark position, the airplane hasn't got a clue where it is. With aligning, the flight management computers are zeroing in on the position of the airplane. It is vital that the airplane doesn't move during aligning, so always make sure that the parking brake is on. And once the alignment is complete, the airplane knows very precise where it is. But the position that it has itself aligned to is not yet connected to a coordinate on the globe. For instance, if you have a navigation system in your car, you start up your car and then, well, if you go to the navigation first, it might say, well, searching for satellites. And then all of a sudden it says, bing, I have aligned myself with the satellites, you are here. And it gives you a spot-on location of your present position. The airplane doesn't have that luxury. We have to tell it where it is, and that's being done on the POS init page. POS init means, of course, position initialization. And if you press the button, you get to this screen. In the screen, you have the field ref airport, gate, set IRS POS. For the ref airport, you always enter the ICAO code of the airport where you at. And ICAO code, every airport in the world has a code that consists of 4 letters, at least every major airport. And for Amsterdam, that is Echo Hotel Alpha Mike. So Echo Hotel Alpha Mike. And you enter that in here. And why is it Echo Hotel Alpha Mike? Well, it's in Europe, Holland, Amsterdam. And basically, by the first 2 letters of the ICAO code, you can already tell in which country the airport is. Because every airport in a certain country has the same first 2 letters. I believe there's a slight difference within the United States, where some airports start with K. For example, New York, John F. Kennedy, that's KJFK. But Anchorage in Alaska is Pank. Papa Alpha November Charlie. So there's something down there that I don't really know much about. But anyway, in Europe, the first two letters always indicate the country. Great Britain is Echo Golf, Germany Echo Delta, Europa Deutschland. France is LF, l'Europe France. So you can already tell a lot about that. Anyway, when you enter the reference airport, you will get a coordinate. And this coordinate is the general coordinate of the airport, but it is not necessarily the position of the aircraft. In fact, I think in 999 out of 1,000 times, this is not the current position of the airplane. And of course, if we gonna tell the flight management computer where the airplane is, we do want the coordinate where the plane is exactly and not this one. Because if we enter this one, there will be an offset on the nav display here. So what we do is we press the next page. We go to page 2 of 3, so next page. And there is the position reference page. For FMC POS, IRS left, IRS right, GPS left, GPS right, and radio. And under GPS left, there is a coordinate. And this coordinate is the last known GPS coordinate to the aircraft. So if the aircraft is properly aligned on all flights, then this position will always be correct and be the present position of the airplane. So we press the left selector key. This coordinate moves to the scratch pad. We press previous page and press the right selector key behind set IRS POS. And now we have the airplane, or the flight management computers know where the position of the airplane is. And you can see that although it's quite close to the general airport coordinate, it is definitely not the same, because 18.4, 18.7 and 45.8 versus 46.2. Once the plane now is aligned, it knows that it is on this location, so we are probably gonna have a very good navigation. If you mess up this phase of the FMC programming, it will affect the navigation, at least the lateral navigation of your entire flight. So this is a vital step. That's why I take so much time to explain it, for successful navigation. Well, we're done with that. So the POS init is now complete, and once the IRS is aligned, we see a normal PFD and a normal nav display. For now, we're done. We're gonna program the route that we will fly. And for today, I have made a route flying from Amsterdam to Bristol in the UK. I use Professional Flight Planner X for my flight plans. And this will be the route to Bristol. We are KLM 1049er today. The route will approximately take 55 minutes for us to fly because the wind is from the east, so we have a tailwind. And well, let's program that. So it's KLM 1049er from Amsterdam to Bristol, which is Echo Golf Golf Delta. KLM 1049er. And we will be departing Amsterdam from runway 9 and also arriving in Bristol on runway 9, so that's easy. Runway 9, and enter that in here. Here is the co-route. Now what is that? That is company route. If you have made a route, it is possible to save that route in a map in your X-plane directory. I don't really use it because, well, basically programming the FMC is one of the nice parts of flight simulation. But if you store your routes, you can give them a name, and if you enter that name in here, for example, EGGD AHAM01, then it will automatically load up that route. So I've not done that. I think it's not very educational in this video. You don't learn too much from it. So we're gonna program the route ourselves. So go to the route page. Now here we have two values to be added for our route, the via and the to, or via and to. Why is that? Of course, we have a huge sky over the Earth. But can planes fly everywhere they want? Well, the answer is basically no, they can't. Because planes fly at a very high speed, it is of course very dangerous if they come very close to each other. So to prevent that, the civil aviation authorities have made aerial routes, which are basically highways in the sky. And you enter the name of the highway here and the name of the nav aid here. And I can best explain that by stepping out of the plane and back into the car again. Suppose you live in England and you want to drive from, let's say, London to Liverpool. If you drive from London to Liverpool, you can drive via the M40 highway up to this position, which is Bromsgrove. If you had the FMC in your car, then you would enter, or basically it is not even Bromsgrove, it is, let's say, Hockley Heath. Then you would enter via the M40 to Hockley Heath, and then you have to go over the M42 to Bromsgrove. So then it is via M42 to Bromsgrove. And then it's the M5 up to, let's call this one, what shall we name it? Wigmore. Wigmore. So then it's M5 to Wigmore, and then it's the M6 all the way up to Warrington. So you dial in M6 to Warrington, and then you have the M62 into Liverpool. So M62 Liverpool. Of course, in the sky we have different names for the routes, and I can show you them in Professional Flight Planner X. If I switch on the, for instance, lower airspace airways, here you will see all these triangles, which are navage, and all the lines with names that are basically the highways. Now, the highways, they run from beacon to beacon, basically, and in between there are nav aids, or intersections they are called. First thing you have to do is you have to get from the airport onto a highway, and to do that you use SIDS, and SIDS, or Sierra India Delta, stands for Standard Instrument Departure. And the departure that we have to fly is mentioned in our flight plan, because it says we're going to fly the Falk 3 Mike, or Falco 3 Michael departure to Falco, and Falco is located here. So that's where we want to go first. So we go to this one, and then we have to go to the departures arrival page. Departure, select a runway, runway 9er, and we add the Falco 3 Mike departure. Go back to route page, and now it says via Falco 3 Mike to Falco. So that's step 1. The Falco 3 Mike to Falco is now programmed. And then we follow the Uniform Lima 9080 to Lamborn, and Uniform Lima is an upper route, so Uniform Lima from Falco all the way down to Lamban, which is down here. So we enter Uniform Lima 9080, was it right? Yes. To Lamban. And then we fly along the Uniform Lima 179er, which is this one, to Compton. So Uniform Lima 179er to Compton, or Charlie Papa Tango. And from Compton we fly the Bravo Romeo India 1 Charlie arrival route into Bristol. And to program that, we have to go back to the departure arrival page. Go to the arrival. We know we will land on runway 9er and we'll use the ILS. And we're flying the Bravo Romeo India 1 Charlie. So select that one. Go back to the route page. And now the route is programmed. But as you can see, I only dialed in from Falco to Lamso, but in between we have a lot of nav aids. It's from Falco to Gorlo, Gorlo to Refso, Refso to Logan, Logan to Tripo, Tripo to Sabre, Mango, and so on, and so on, and so on. So how do we check if the route that we have entered is now correctly in the flight management computer? We do that on the legs page, because every stretch between two nav aids or two intersections is called a leg. So it's the leg from Falco to Gorlo, it's the leg from Gorlo to Refso, it's the leg from Refso to Xaman, it's the leg from Xaman to Logan. And on the legs page we can see all these individual legs. So we started with the standard instrument departure, so we have to fly to Echo Hotel 030, then to Echo Hotel 025, and it gives quite a lot of information, this page, because it says the name of the waypoint, the heading you have to fly to reach it, and the distance you have to fly to reach it. So this is the distance between two points. This is the heading you have to fly that distance on. And now sometimes you see comments on the right side of the screen. This row, or column, I must say, gives you the speed. So at Echo Hotel 030 we have to fly at 220 knots. And well, 500 means 500 feet or above. And let's see if they have more of that. Yes, at Compton we have to be flight level 220. At Pomax you have to fly at 250 knots, as it says right now. And when we are near the airport, the outer marker for runway 9er, we have to be 2500 feet or above. At runway 9er we have to be at 679 feet, which corresponds almost to the aerodrome elevation of 622 feet. And if we miss, we have to climb to the missed approach altitude of 3000 feet. So that's all information that you can find in the legs page. And on the legs page, you will check each and every page for route discontinuities. So let's see if they are mentioned here. They're not. Falco, they are not. They are not. They are not. And it's not here as well. So we now have entered a route from A to B. We have checked if all the legs in between are correct and if they are all connected to each other, that there are no discontinuities, because a route discontinuity means that there is a gap in your flight plan, that you say I want to fly to position Y and then I want to fly to B, but the then has gone. I hope that's clear. You will sometimes get them, especially you have to be especially carefully when you insert departure or arrival routes. But we have programmed it now and they are not there, so that's good. So we press the activate and execute button. So now this route is completely stored in the flight management computer and the computer knows that it will fly this route today. This entire process of getting from A to B is what we call lateral navigation. It's the navigation over the surface of the Earth, or as you might know, LNAV. But there's another button that says VNav, vertical navigation. And vertical navigation has everything to do with the performance of the aircraft. And that's not yet calculated because for the performance of the aircraft, we need details about weight and balance and about weather en route and stuff like that. So let's go back to the init ref now. And on the active performance initialization, we have to enter a number of values. First of all, according to our flight plan, we have a zero fuel weight today of 39.4 tons, 39,413 kilos. So let's make sure that the airplane knows that. 39.4, go to ground surfaces, 39,908, so slightly less. I think 38 is sufficient. Well, let's say 48, be on the safe side. So that's set now. And the flight plan also tells us that for fuel, on release of the flight, we need to have 4,781 kilos of fuel on board. 4781. So 478, if you round that off, it will be 4.8. Dial that in there, and then you can either do it realistically or instantly. For the video, I do it instantly. So now we are loaded with fuel, and the zero fuel weight is correct. These values of the airplane we have to dial into the flight management computer because it has to calculate with them. So in the zero fuel weight, we enter 39.48. And now you see that the gross weight is automatically filled because gross weight is nothing else than the zero fuel weight, and you add up the fuel on board with that. So 39.5 plus 4.8, that's about right, huh? Gives us 44.3, and voila, there it is. Reserves, you can dial in the amount of fuel that you want to have in reserve when you reach your destination. Now, I always put in 2 tons here, so 2,000 kilos. And here is the cost index. Now, the cost index, what is that? The flight management computer uses a formula. And with that formula, it can either fly very fast and very inefficient fuel-wise to a destination, or it can fly highly fuel efficient but much slower to the destination. And you can tell the computer which you want by entering a number here. And I don't have the entire formula. If you want that, look it up. It's probably to be found somewhere. I don't know it, and I don't really want to know it. But I do know that KLM uses in the 737-300 a cost index of 30. So I dial in 30. And now the flight management computer will calculate with the formula where the cost index variable is set to 30. So it's reasonably fuel efficient, but not too slow. And then finally, we have to dial in our cruise altitude, which today happens to be flight level 360. So we enter 360. And flight level 360 means nothing else than 36,000 feet. A flight level is basically 1% of your altitude in feet. So if you fly at 6,000, you fly at flight level 060. If you fly at 4,000, it's flight level 040, and so on and so on. If you have it, you can enter a cruise wind variable in here. Well, I don't really find it that exciting on the short haul flights. I tend to take enough fuel on board for a flight, so I usually leave it blank. But you can do it. You can also add temperature information, etc., and the transition altitude. Transition altitude is set to 5,000, and in Amsterdam, I believe that is correct. Or is it 3,000? I'm not really sure now. Let's look that up. So EON transition altitude. And the transition altitude, by the way, is the altitude at which you switch from the actual barometric pressure of the airport to the general or standard QNH setting, and it's 3,000 feet in Amsterdam I'm reading here. So let's see if we pick out a chart for the SIT. Falco 3 mic chart. So let's look it up. It's not in here, I think. Well, I'll just look up transition altitude 3,000 feet in Amsterdam. So let's dial that in. So, and again, execute, because now the flight management computer knows that all the input we gave is correct and we want it to work with it. That's why you execute it. If you don't execute it, it doesn't work. Then we go to the N1 limits page. N1 is the power of the engines, basically. And when we take off, we can do two things. We can either slide the throttles all the way forward, and that will cause the engines to run at full power. But when something runs at full power, the wear and tear is huge. And that, of course, decreases the lifespan. Now, an airplane engine is a very, very expensive part of an airplane. So if you bought one, you want to use it for as long as possible, meaning you don't want to stress it out too much. And therefore, we are given the possibility to derate. What is that? Derate means that you downsize or downscale the power at which the engines run. Is that correct? Well, yeah. Let's. I hope that's. Well, let me explain it to you. Go back outside the airplane. If you look at the airport, and we have the runway, that runway is quite long, and the airplane is quite small. If I'm starting on this runway and I switch the throttles slide the throttles all the way forward at full power, then it could very well be that I reach this part of the runway and can already fly away. But that leaves all these runway length unused. So if I gave my engine less power, it would take longer for it to reach the rotation speed, but it's still safe because we still have enough runway to do that. And if I let my engine run at less power, the wear and tear is less and the lifespan of the engine is longer, and that is what you want. So basically, you are always trying to calculate the optimum setting for, well, within the safety margins, of course, use as much as the runway as possible, because then you don't overstress the engines. So it's very economical. But it is very, very important. Of course, the profit margins in the aviation industry are extremely low, so every penny is welcome. And that's what you do with derating. So let's go back. And derating can be done by adjusting the temperature. Of course, there is a real world outside temperature, which is 3 degrees Celsius today. It's slightly above freezing. 0 Celsius is freezing point. But if we say to the engine that it is actually much warmer, the engine will use much less of its power. So if I'm telling it that it is 37 degrees out there, which is nice and warm, it says, hey, now I only need 86.3. While previously it says it needed 89.7. And if you do that on every takeoff, and a 737 does a lot of takeoffs each day, that's definitely gonna increase the lifespan of the engine. And you can also do it much higher or lower, but let's say 37 degrees. So that's okay for now. You can also say I want to derate and just take the takeoff 1. That's also possible. You can also tell the computer that you don't want to climb as fast. I mean, the steeper you climb, the more engine power you need to maintain a certain speed. So if you make your climb less steep, you need less engine power. So that's also reducing the wear and tear of the engine. That's what this page is for. But we have set it as we want, and we go to the takeoff page. And at the takeoff page, you can set actually only one variable, and that is the flaps. Flaps are usually put to 5 at takeoff in a 737. If you have a bigger or heavier airplane like the 747, which is, well, if it's full of passengers, full of fuel, it's of course very heavy, they will use usually flaps 20 for takeoff. But the 737 is fairly small, fairly light, and flaps 5 is enough. But what are flaps? Flaps are positioned on the rear end of the wing, and also the leading edge slats are on the front of the wing. If you set flaps 1, these will slide forward and these will slide 1 backward. Why is that? Well, that has to do with how an airplane flies. And how an airplane flies is, of course, dependent on how the wing work. Because without wings, the plane can't fly. So there's something happening around the wings that causes the plane to fly. Now, what is that? It's very basic, very short, maybe not entirely correct, but it's just for a basic understanding. An airplane flies because of the lift principle that was discovered by a French dude named Bernoulli, or at least I thought he was French, it sounds French, and it has to do with the shape of the wing. If you look at the side of the wing, you see that the shape it is quite flat at the bottom and then rather curved on top. And because it is curved on top, it causes the air that flows over the wing to flow faster than the air that flows beneath the wing. If the speed of the air above the wing is faster, it means that the pressure on top of the wing is lower. So you get a pressure difference. The pressure of the air below the wing is high, while the pressure on top of the wing is low. And air, just like water, has the characteristic that it will always flow from high to low. Water flows from high terrain to low terrain. Air always flows from an area with high pressure to an area with low pressure. So, Bernoulli said, if you place the high pressure area below the wing and the low pressure area above the wing, then the air wants to move to the top of the wing. On its way, it will find that there is metal and it will just lift it up. And if it lifts up the metal, then it will lift off the metal of the wing. Then if the wings are strong enough, they won't break, but it will lift off the entire fuselage of the airplane. And that's basically how an airplane flies. But for that lift to occur, because that upward force is called lift, the plane needs to reach a certain speed. And that's why a fixed wing aircraft needs a long runway, because it needs to gain speed. And a helicopter can fly from its own position, because on a helicopter the wings rotate, while on a fixed wing aircraft, of course, the entire aircraft has to move. The amount of drag that is being generated is dependent on three major things. It's of course speed, but the speed is dependent on the curve of the wing and the surface of the wing. Flaps do two things. Because they are, when you move them down, they will increase the curve of the wing and they will increase the surface of the wing, which means that the wing generates lift at a lower speed than if the flaps and slats are retracted. And that's why we use flaps. Because if you don't use the flaps, then the speed at which the wing can fly is much higher and you need far more runway length to reach it. But there is a downside to that, because if the flaps are extended, they also create drag. And drag is something that you don't want on an airplane because drag costs speed and it uses a lot of fuel. It has to use a lot of fuel to overcome the drag. So the airplane engineer said, well, let's make movable surfaces that will increase the surface area of the wing and the curve of the wing when we need it, and that we can retract so they don't give drag when we don't need them. And that's why on landing you see the flaps extend so you can fly slower, and during cruise the flaps are up so they don't create drag. That's basically the point of flaps. In a nutshell, oversimplified but kind of correct. But anyway, on takeoff we use flaps 5. If we were to set, for example, flaps 10, you will see that the speech will go lower. And that's an invalid entry basically. Let's say we don't use flaps, then you will see they are higher. Why is that an invalid entry? No, cannot delete it. It's just flaps 5 on takeoff on this bird. Flaps 2 maybe? No, that's not very real. In real life you can adjust this and then you will see that the speeds move. But anyway, 119, 121, 131, and then you will set them of course on the speed box, but hey, that's not what we are for now. So now we have programmed the route, and we have programmed the weight and balance of the aircraft. We have calculated the V speeds. And V speeds, what are V speeds? V speeds are critical speeds. We have three: V1, VR, and V2. V1 is the most critical of all the speeds. It means if you have not reached V1 and something happens on the airplane, for instance an engine failure, there is enough runway length available to safely stop the airplane. If you are over V1, whatever happens, you will fly. You have to fly because you don't have enough runway to slow the airplane to a complete stop. VR is the rotate speed, and that's the speed basically at which the wings generate enough lift to just go to the sky safely. And then we have V2. V2 is the speed at which the airplane is still able to fly if one of the two engines fails. Therefore, our climbing out speed has to be higher than V2, because if we are flying at exactly V2 and the engine, one of the engine fails, then at first the speed will drop back. But if the speed drops back too much, the wing doesn't generate enough lift and will stop flying, causing the plane to just fall from the sky, and we don't want that. So in real life, on the indicated airspeed on the mode control panel, you will always dial in 131 plus 20 knots, so in this case 151. That's basically the story behind V speeds. So we now have gross weight, cruise altitude, we have our route. We want to climb to flight level 360 at a speed of 282 knots or 0.727 Mach. First waypoint is 220 knots. At cruise we will fly flight level 360, while the optimum altitude for the plane to operate is flight level 370. But there's a rule in aviation: if you are flying westbound, you have to fly at an even flight level, and if you fly eastbound, you have to fly on an odd flight level. That is to prevent planes from flying into each other frontally. We have target speed of 0.734 Mach, and the engine N1 will be 81.3%. For the descent, target speed for the initial descent is 280 knots, and the descent will be programmed and adjusted later on if you are actually descended. And that's also very dependent whether you can descend using the CDU or you have to manually enter the air traffic control commands in your mode control panel. The legs page we already checked. Departure arrival, well, we used that already. There are no holdings we have to do, so let's check the progress page. And on the progress page you can see the total distance to Bristol, which is, according to our programmed flight, 309 nautical miles. Let's check that with our flight plan. It says 305 nautical miles. So there's a little, well, this is mainly a program that is actually built for Flight Simulator X and prepared, or actually Flight Simulator X and not for X-Plane. So there's always a slight offset, but it's about right. We don't have to do anything on the N1 limit because we already did that. We don't have to program any navigational fixes. So we are done with programming the flight management computer. That's actually what you do on programming the flight management computer before a flight. I hope that this is clear now. And of course, if you press the LNAV and the VNAV buttons, they give the signal to the flight management computer to follow or use the information that was entered in the CDU to perform the flight. So that's basically it. I hope that this tutorial was clear. If I messed up on certain points or told things that are not true or completely accurate, feel free to leave a comment and tell us what was wrong and why it was wrong, and also tell us what is right, of course. Yeah, that's basically it. Well, there's one thing that I wanted to show you, and that has to do with the legs page. As you can see on the nav display, the route is now shown. But if you want to check if the route is set up correctly, you can use a knob, which is down here, to switch from the map mode to the plan mode. And if you do that, the nav display doesn't center around the position of the airplane, but it centers around the position of the waypoint. So you can basically walk through your route and see if you programmed everything correctly. When you set it to plan mode, in here we'll enter the step button, and you can use the lower right line selector key to step through your route. So from there to there, to there, to 40, to Falco, Gorlo, Refso, Xamon, Logan, Tripo, Sabre, Mango, Braso, Wesul, Lambin, Compton, Pomax, and then in the approach around Bristol. That's a very handy trick. Use that always to check your route and especially your arrival route. So that's it for today. That's it for this video. Hope you like it. As I said, feel free to leave a comment and see you next time. Bye bye.